Welcome back, everyone. We have the fourth talk of session 3, and our next speaker is Aparajita Karmakar from ISI Kolkata, and she will be speaking on equivariant cohomology of projective spaces. Yeah, over to you.
Thanks, Shomo, for the introduction. And I'm thankful to the organizers for inviting me to give a talk here. So I'll start. The title, as you can see, is Equivariant Cohomology of Projective Spaces. So the goal is, in usual cohomology, when X is a CW complex with even cells, for example, CPN, CP infinity, its cohomology is torsion-free and indexed by the cells. So for each cell, we have a generator. Our goal is to find a similar result in the equivariant setup. So what is the equivariant setup? So in this setup, instead of spaces, we deal with G spaces. That is a space equipped with a G action. The nice spaces in this category are the GCW complexes instead of CW complexes. And the equivariant cohomology takes into account the G action on the space. It is denoted by H bar. Alpha denotes the grading, G denotes the group action, that X is a G space, and M, here M is a Mackey functor. So the cohomology is denoted by this sign, and it itself is a Mackey functor. So the cohomology is a Mackey functor valued, and can be graded over ROG, which is the Grothendieck group completion of real orthogonal G representations. So what is a GCW complex? It's a G space X with a filtration Xn. The zero cells are union of orbits of G. And Xn plus 1 is built from Xn via this following push-out diagram. So it's the same thing. Dn is attached to Xn plus 1 via the attaching map, but we also have the G mod H beta for beta varying actions. So the cells of this GCW complex does not look like Dn, but copies of Dn together attached. And all those Dns have a permutation action that swaps one or two of them amongst them. So, for example, let G be C2 and sigma denote the sign representation of C2. Then S sigma has two cells. One is C2 mod C2 union C2 mod C2. So the zero cells are the North Pole and the South Pole. And although in the diagram, you can see two copies of D1, but we call it one single cell. So this is C2 mod E cross D1. So it has two zero cells, C2 mod C2, and one cell, C2 mod E cross D1. However, this GCW structure is not always useful. For example, equivariant complex projective spaces can be thought of as generalized G cell complex, and the cell structure is as below. So what is a generalized G cell complex? It's a G space X, again with a filtration Xn, where X0 has only one orbit, that is G mod G, and Xn is built, n plus 1 is built up from Xn by attaching cells of the form dV along the boundary SV, where for a G representation V, dV denotes the unit disk V, and unit disk in V, and SV is the unit circle in V. So in GCW, in generalized GCW complex, G cell complex, what we do, we take a representation and look at its cells, look at the DNs in the representations. So that already gives a G structure on the cells. That's how we form a generalized G cell complex. Okay, one important notion is Mackey functor. So for G equals to Cn, that is Cn is a cyclic group of n elements. A G Mackey functor M consists of a commutative G mod H group. That is M bar of G mod H is a group, is an abelian group, and M bar assigns an abelian group for every G mod H. There is a transfer map from G mod K to G mod H, and a restriction map from G mod H to G mod K, where K is inside H, is inside G. So these few informations are required when G is Cn to define a Mackey functor. And these restriction and transfer map have some relation amongst them that they need to satisfy to become a Mackey functor. A constant Mackey, in our examples, a constant Mackey functor is very important. So I'll describe. So the constant Mackey functor Z bar assigns Z, the group of integers, for every G mod H. The restriction is identity for every two subgroup, and the transfer map is the index of the smaller subgroup inside the bigger subgroup. So for G equals to Cp, Z bar Cp mod Cp is Z, Z bar Cp mod E is Z, and the restriction and transfer map is shown in the diagram on the right side. As you can see, the index is P. Okay, what is equivariant cohomology? So for a G spectrum X, the equivariant homotopy groups have the structure of a Mackey functor, where for every G mod H, pi G n bar X of G mod H is actually the homotopy, nth homotopy group of X power H. X power H is the H fixed points of X. As we know, X is a G space, so we can think of the H fixed points of X. The grading N may be extended over alpha in ROG, the real representation, the orthogonal real representation ring of G, by defining pi bar G alpha of X at G mod H. So pi bar G alpha of X is a Mackey functor. It takes what is the value at G mod H? It's the morphisms in the homotopy G spectra category. The morphisms between S alpha smash G mod H plus and X, which turns out to be isomorphic to pi H alpha of X. We have this theorem by Lewis, May, and MacLeod that for every Mackey functor M, there is an Eilenberg-MacLane G spectrum HM. So this is analogous to Eilenberg-MacLane spaces, how we find that for every cohomology theory, there is a spectrum. So for every Mackey functor M, there is an Eilenberg-MacLane G spectrum HM such that its value at n equals to 0 is M bar and 0 otherwise. And this G spectrum is unique up to isomorphism. This is an important theorem by Lewis, May, and MacLeod. Thus, we may define cohomology and homology theory associated to Mackey functor, which are ROG graded. And the description is, we have to go to the homotopy G spectra, homotopy category of G spectra, and see the morphisms between X and suspension alpha of HM bar. That we will call the cohomology of alpha cohomology of X with Mackey functor M. And the homology will be defined as the morphism group in homotopy G spectra category. And the morphisms will be between S alpha and H/HM. For constant Mackey functors, the integer graded groups at the orbit G mod G compute the cohomology of X mod G. So for constant Mackey functors, things become a little easier. And X mod G is the orbit space of X under the G action. So our main results that we found out are mainly freeness theorems, and the basis of those theorems are comes from paper by Lewis. Let us see what is the freeness theorem. So let X be a pointed G space. The cohomology H of X is said to be free as a H star G S naught module if H star Gx is a direct sum of H star G S naught modules of the type. So H star Gx is basically sum of H star Gs naught, but it can be shifted by some alpha. So suspension alpha H star Gs naught is also an H star Gs naught module, and H star Gx is some of those kinds of modules. So the theorem says, let G be a cyclic group of square free order and X be a generalized G cell complex having even dimensional cells which are attached in proper order. So this proper order is quite important in all the calculations. Unless we achieve the proper order, we won't be able to get a freeness theorem. This proper order ensures that we get the connecting map while calculating the cohomologies to become 0. Then H star Gx plus with A bar, here A bar is the Burnside ring coefficient, is free as H star G S naught module. Moreover, the generators are in 1:1 correspondence with the cells. So this is kind of a similar result as we got for CP infinity or CPN in usual topology. This proof is uses induction on the skeleton. Okay, so how does the proof go? We consider the cofiber sequence xn plus 2, xn plus 1 plus 2, SV. Since xn, this is a generalized G cell complex, and xn plus 1 is formed by attaching the disk of what do we say? Disk of a G representation V. So as we look at the cofiber sequence, we get the SV. Then the associated cohomology long exact sequence is this, where del is the connecting homomorphism. The main step of the proof is to observe that the proper cell attachment forces the boundary map del to be 0. So this proper cell attaching is important. Limitations in the case of Burnside ring coefficients. So Lewis's theorem is given for Burnside ring coefficients as the Mackey functor. but there are some limitations. With Burnside ring coefficients, this approach cannot be further generalized to obtain a freeness theorem for groups like CP square or anything that contains CP cross CP. Thus, yeah. But in the case of Z coefficients, this obstruction due to the attaching map vanishes, as we have the following theorem. Sorry. So this theorem helps us with to make the attaching map 0. So alpha is in ROG and mod alpha is odd, and its H fixed points, the dimension of its H fixed points is less than 1, implies dimension of its K fixed points is less or equals to 1 whenever H is a subgroup of K. If this condition holds, then the cohomology at alpha grading of S0 is 0. Note that a version of this theorem was earlier proved by Basu and Ghosh for Cn where n is odd, and this theorem extends the result for any n. Yes. So for a general cyclic group G equals to Cn, the irreducible complex G representations are one-dimensional, and they can be given by 1 lambda, lambda square up to lambda to the n minus 1, where lambda is the lambda acts on V or C via nth root of unity. And let U be the infinite sum of lambda I, and we want to find out the cohomology of PU. We didn't. What is PU? It is the equivariant complex projective space. A proper cell attachment may be built up by successively attaching cells of the form DWK, where WK is lambda K inverse tensor with sum up to K 0 to K minus 1 of lambda I's. This is necessary, as again we can see this condition, this proper attaching condition will help us to attaining the zero group as the cohomology of S0. Therefore, the attaching map will be 0. An additive decomposition is obtained with the help of above mentioned theorem. So HZ smash PU is disjoint union is wedge sum of HZ smash SK mu plus phi I, where phi i's are the lambda minus I plus up to lambda to the minus 1, and mu is the regular representation. So we found out some additive decomposition for PU, and we will see the ring structure of PU as well. So for G equals to CP, where P is a prime, we already have H star CP PU Z bar is H star minus K mu minus L lambda of S0 with Z coefficients, their direct sums. There are classes alpha lambda in H lambda G PU plus and alpha mu in H mu. So we have the additive cohomology and the alpha grading. In the lambda grading, we have the class alpha lambda, and in the mu grading, we have alpha mu that generate the whole that generate the whole cohomology of PU plus. Note that this theorem is for n equals to P. As an algebra, this cohomology H star CP of PU plus is an algebra over H star CP of S0. more precisely, we can write it as H star CP S naught Z bar generated by alpha lambda and alpha mu, but they have a relation between them, U lambda alpha mu minus alpha lambda into A lambda plus alpha lambda to the P minus 1. These U lambda and A lambda are elements of H star CP of S naught. This proof is obtained by using restriction to various fixed points using the idea of Lewis. The cohomology ring structure. So we already have the classes alpha lambda and alpha mu for G equals to CP. But when G is Cn, sorry, there is a typo here. So in the alpha mu belongs to H mu Cn. So Pu plus Z. And also we can find another class alpha phi D belonging to H phi D Cn of Pu plus Z bar. So we have three kinds of elements. At the lambda degree, we have alpha lambda, mu degree alpha mu, and phi degree alpha phi D that generate the cohomology of Pu plus as an algebra over cohomology of S naught. The relations here can be found amongst alpha lambda, alpha mu, and alpha phi D, but they are a bit cumbersome, so I haven't put it here. For further exploration in this area of equivariant stable homotopy theory, one can try to find similar results in the case of abelian groups instead of looking at cyclic groups only. The challenge will be to find out theorems that will help to show that the connecting map is 0. So in this case, in Z bar coefficient, once we shift from Burnside coefficient to Z coefficients, we have the theorem which ensures the connecting map is 0. But for abelian groups, we don't yet have. So this can be a way to explore further. And also we can think of Stiefel manifolds, equivariant Stiefel manifolds, try to give a GCW structure on it, and then find its cohomology, try to find its additive and ring structure. So these are the references. Thank you.
Thank you, Aparajita, for the very nice talk. Any questions? If not, let us thank the speaker. Thanks a lot.